So next is very important concept. So the electrical system is given. Okay, the electrical system is given, and its signal flow graphs also given. So signal flow graph also given. What we have to do? We have to find. Okay, so the value of G2, what from the signal flow graph, they are asking the G2 value. Okay. So from the electrical circuit, say this circuit A, circuit B, so B. From the circuit A, we can take apply Kirchhoff's voltage law. So from circuit A, apply Kirchhoff's voltage law in the first loop. So applying Kirchhoff's law in the first loop. What we are getting? V1 V in of S, V1 of T S equal to. So I1 is at 1. I1 is at 1 plus or simple, we will take a letter. I1 is at 1 plus I is at 3. Okay, I1 is at 1 is at 3. So is at 3 into I1. Actually, when we apply, take a Kirchhoff's voltage loop in the first loop, I1 is at 1 plus Z3 of I1 minus I2. Okay, so from this equation, what do we get? V in of S, applying Laplace transfer function. What do we get? I1 of S equal to Z1 plus Z3 minus I2 of S Z3. Okay, so from this relation, what is I1 of S? I1 of S is V in of S divided by Z1 plus Z1 of S plus Z3 of S, Z3 of S plus I3 of S into Z3 of S, sorry, I2 of S into Z3 of S divided by the denominator Z1 plus Z3. Similarly, apply the Kirchhoff's law for this equation, we'll be getting I2 of S. Okay, sorry, what is I2 of S minus I1 of S into Z3. So in the Z3, I2 of S minus I1 of S plus I2 Z2 of S plus Z4 I2 equal to 0. So if you manipulate this relation, we will be getting I1 of I2 of S. From this relation, I2 of S equal to Z3 divided by Z1 plus Z3 plus Z4. Z3 plus Z4. Okay, Z4 into I1 of S. into I1 of S. So I2 equal to Z3 of S, Z3 of S. You add S for all the terms. Z3 of S divided by, so I2 of S. So I1 of S equal to I1 of S equal to V in of S, V in of S divided by Z1 plus Z3 plus I2 Z3 plus I2 Z3 divided by Z1 plus Z3. Equation number 1, I2 of S equal to Z3 divided by Z3 divided by Z1 plus Z2 plus Z3 into I1 of S. So equation number 2. Okay. Now let us do analysis for from the circuit B from the signal flow graph shown in figure B. What is here? So from this figure, you can able to find I1 and I2. What is I1 here? So I1 is nothing but G1 times Vin. So this gain into input. So I1 equal to G1 times Vin. Not only this I1 is also equal to this plus the I2 also coming to I1 plus positive feedback plus I2 into H. I2 into H. From the signal flow graph, I1 equal to G1 into Vin plus I2 into H. So keeping equation number 3. Equation number 3. What is I2? I2 of S is nothing but, see, what is I2? I2 is nothing but only this G1, G2 into V. G1, G2 into V. Or simply G2 into V. Okay, G2 into V. So that is I2. G2 into I1. So I1 comprises of everything, right? This is the input to G1. Sorry, G2. So I2 equal to G2 into I1. That is in the equation number 4. So I1, I2 is given. So just compare on comparing 1 and 3 and 2 and this is electrical network. This is from signal flow graph. So both are I1 and I2. So comparing 1 and 3, we will be getting. So what are the coefficients? So when comparing this and this, so G1 equal to 1 by Z1 plus Z3. Okay. Similarly, on comparing 2 and 4, so what is 2 and 4? I2 equal to I1 coefficient G2. So G2 equal to Z3 divided by Z1 plus Z2 plus Z3. So this is G2. This is the required solution for the problem. Very simple. If you understand the concept, then it is very easy. Okay. Next is, so you take it as an assignment for this. This is assignment. So please do yourself. Okay, assignment. Understand? Next is block diagram reduction and signal flow graph methods. So block diagram reduction and signal flow graphs. What are the important points to be remember in the block diagram reduction? So when two blocks in parallel, sorry, series, blocks in series, the net gain is G1 and G2, product of two. If two blocks in parallel or cascaded or adding, say G1 and G2, clear? Plus, then the resultant will be G1 plus G2. Suppose if it is minus, here is minus. Okay, so then feedback. If it is feedback, so see, input is R, output is C, R, C. If it is in feedback part, okay, G, H, so feedback path. So everything we discussed in the last class. Okay, just point is plus, minus, and C, R. This is forward path divided by 1 plus feedback path. This is the resultant equation. So one important point to keep in your mind, there are two concepts. One is takeoff point or branch point. Other one is summing point. If the summing point is ahead of the block, suppose if the summing point is ahead of the block, okay, say this is R, say P, this is C. If the summing, this is called summing point. If the summing point is ahead of the block, if you want to shift after that, if you want to shift in some situation, if you want to shift after the block, then the gain is not altered. Okay, the same gain value is placed. That is G. Now we are putting the summing point here. So what happened? We say P. The same G is here, right? Whereas in the takeoff point, another point is there, that is G, takeoff point. Okay, say R, same R is here. So if we shift the takeoff point from here to the after the G, after the block, so what do you have to do? This is reverse, vice versa. Okay, so the summing point, the junction point, takeoff point, and the summing point, one under inverse manner. In the gain alteration, you see R, we should get same R here, say R. So if you want to get same R, what we have to do? Here we have to put on gain, that is 1 by G. So if we shift from summing point from here to here, gain is same. In the same, suppose if shift from after the point to front point, then gain will be 1 by G. If you shift the breakaway point from before the block to after the block, we have to introduce gain of 1 by G. Suppose if you shift the gain here to before the ahead of the block, you have to simply put G. Okay, this is the simple points to be remembered while doing the signal flow graph method. So this is the simple example for a block diagram. So how to reduce this block diagram using the block diagram reduction techniques. So first you look into this, what we can do first here. So this is adder. So this is adder. This is also adder. This is also adder. This is the negative feedback. This is the feedback. Okay. So feedback system. So what you have to do? See here. If we shift this takeoff point from before block to after block, then this will be very simple. So first step one, okay, what we have to do here, shifting this point from here to here. When you shift this point after this block, so what happens if you shift before to after, what you have to do, 1 by the gain. Understand? Very simple. So this block is, this value become 1 by G. Say simply put. So now the block is reduced. G1, G2, G3. Okay. So now when we shift this point to here, okay, we shifted here. Now this feedback, this feed forward gain becomes division G4 divided by G2. We have to divide this gain by this to shift this point. So G4 by G2 plus. Now we can easily simplify this these two adder. Okay, these two adder. So how do you add these 2 points? Say G3 plus G4 by G2. This is the resultant gain at this juncture. Okay, so we draw. So R plus minus here G1 so across G1 there is a feedback path H1 clear. So this is G1. So now G2 is here. This point is shifted. So G2. So G2 clear. After shifting this to here G2, this gain, the total gain is now the gain is G3 plus G4 by G2. That's all. There is no feedback path. So C of S. Understand or not? Very simple. Okay, next after G2, there is one more feedback path, that is H2, that is of negative feedback. Okay, now what we can do, we can also shift. You can now we can simplify this block by closed loop configuration. So what is that? G1 forward loop divided by 1 minus feedback loop, because this is positive feedback. So 1 minus G1 H1. So this block, this equivalent is G1 divided by 1 minus G1 H1, right? So after this block and this G2 are in series. So again, you can multiply this block. So this block and G2 block, G2 are in cascaded. Cascaded means series. So multiply these two. Multiply these two values, right? Multiply the two values. What are the two values? So if you multiply that, so the here the entire equation becomes, the block diagram is reduced into plus. So the entire block diagram is reduced to G1 G2 divided by 1 minus G1 H1, okay, plus G3 plus G4 by G2. This is C, this is R. So again one feedback H2, right? H2 is here. So negative feedback. This is negative feedback. Clear? So again, this is consider, this is G, this is H. For this closed loop feedback can be reduced as G divided by G1 plus GH2. Okay, so this comes here. Okay, here at this stage into this. So this value, and finally this G3 plus G4 block are in series. So if you multiply these two, you will be easily getting the transfer function. So C R. So this is G3 plus G4 by G2. Okay, if you multiply this, you will be getting the final answer. Next is how to do in signal flow graph. Okay, so what are the properties in the signal flow graph? A signal flow graph applies to only linear systems. The equations for which a signal flow graph is drawn obey the algebraic equation. It should obey in the form of algebraic equation in the form of cause and effect. Okay, nodes are used to represent a variable. Nodes represent variable I1, I2, I3 like that. The nodes also are arranged. Okay, nodes are arranged from left to right, normally from left to right. Feedback nodes from the direction. The signal travel along branches only in the direction described by the arrows of the branches. The branch directing from node yi to yj represent the dependence of variable yj upon yi, but not in the reverse manner. A signal yi traveling along a branch between nodes, two nodes, yi and yj, is multiplied by the gain. Suppose traveling like this. Suppose it has gain G. Okay. So this is 1, this is another node, 1 and 2. Suppose this is R, this is C. So what is C? C equal to G times R. So this is the case here. So the when the branch between nodes yi and yj is multiplied by the gain of the branch gij, so that a signal gij yi is delivered alone at the node yj. Okay. So using this concept, let us draw the signal flow graph for this. Wherever gain is there, you take between two nodes. So the blocks, the junctions, the blocks are first we make it as node. Okay. First in the forward path we can draw 1, the 2. This is 1. This point is 2. This is 3. This is 4, 5, 6, 7. When there is no gain, suppose between node 1 and 2, no gain. So the gain value taken as 1. So between 6 and 7, there is no gain. So the value is taken as 1. So there are 7 nodes we consider for the diagram. So signal flow graph. Signal flow graph. What is the signal flow graph? First to draw the signal flow graph. 1, 2, 3, 4, 5, 6, 7. So one node is R, 7th node is C. So 1 and 2, there is no gain, 1. So between 2 and 3, between 2 and 3 also 1. Between 2, 3, 4, 5, 6. Between 2 and 3 also gain is 1. 3 and 4 gain is G1. 4 and 5. 4 and 5 gain is G2. 4 and 5 gain is G2. 5 and 6 gain is G3. Then 4 and between 4 and 6 there is a feed forward gain. 4 and 6 between 4 and 6 there is a feed forward. There is a feed forward gain. So G4. Okay, plus. Then between 4 and 3 there is a positive feedback. 4 and 3 there is a positive feedback whose gain is plus H1, not minus. Negative, not negative feedback. Between H1, between 5 and 2 there is a feedback. 5 and 2 between 5 and 2, H2. We should put minus because it is negative feedback. So minus of this. So this symbol is also in the reverse direction. Okay. So minus, then G1, G2, H1, everything is over, right? 5, 6, 4, right? That's all. First, let me introduce some terms called loops. Loops. What are all called loops in the system? Okay, loops. Forward path. Forward path. Feedback path. Feedback path. Loops, etc. So loops we consider as L1, L2, etc. Forward path P1, P2, P3, etc. Feedback path is H1, H2, etc. Okay. What is forward path means? If you start from the starting node and ending at the path start from the starting node to what are all the possible paths, not only a single forward path. There are many forward paths. Starting node and it ends at the ending node. So this is the starting node. This is ending node. So let us see how many forward paths in this signal flow graph. Okay, how many forward paths? See, start from here. You move in the only one direction. You should not return, right? So you see here, 1, 2, 3, 4, 5, 6, 7. So one forward path P1 equal to 1, 2, 3, 4, 5, 6, 7. Good. Okay. Is there any other forward path available here? Any other way? So to go to a place, there are many ways. No. Similarly, I am finding one way. 1, 2, 3, 4, 6, 7. So I am skipping a 5, right? So another forward path. P2 equal to 1, 2, 3, 4, 7. Sorry, 6, 7. 4, 5 I am mixing. So there are two possible paths. There are two possible paths here. Only two possible paths here. Okay. What are loops? Loops are nothing but starting node and ending node will be same. Say for example here, I am starting from 3. I am starting from 3 and moving to 4 and through H1 I am again I can reach the same point. So this I consider as a L1. Clear? One more loop I am going to search. That is, I am starting from the node 2. From here, I am moving 2, 3, 4, then 5. Then I am again coming back to 2 here. So L1 is G1. G1, the loop gain is G1, H1, this L1. The L2 is 1 into G1, G1, G2 minus. So L2 is minus G1, G2, H2. Any other loop available here? Any other loop? Any other possible loops? No, no other loops. Okay. We are having only two loops here. Whether any touching loops available here? Touching loops? Two loops are there. Any non-touching loops? Both loops are touching with each other, right? So you see, you find the common term between this loop. If G1 and G2 is available, the gain is available with both. So non-touching loops. So next is finding the non-touching loops. Non-touching loops. So non-touching loops NTL equal to 0 here. Okay, non-touching loops. So so the two loops are touching with each other. Okay. Also, we have to find any loops available which is not touching. We have to find loops, any loop in signal flow graph which is not touching the forward paths. Any forward paths, not only P1 or P2, not any forward paths. So if that also available, that also we require for analysis, right? So to get the transfer function from the signal flow graph, we are going to study the rule called Mason's gain rule. Mason's gain rule. Mason's gain rule. right? So he states that the overall transfer function, the transfer function of the system equal to 1 by delta sum of, say, k equal to 1 to n pk del k, pk del k. Okay, this can be expanded like this: p1 del 1 plus p2 del 2, okay, plus p3 del 3, etc. pn del n divided by delta. So what we have to find? We have to find the P1 del 1, P2 del 2, P3 del 3, etc. and the delta. So what is Pk? Pk or P1, P2, Pk is the number of forward paths. Number of forward paths. Okay. So what is delta? Delta is 1 minus sum of individual loops. Sum of individual loop gains. Loop gains plus sum of gain product of sum of gain product of any possible two non-touching loop. Any possible two non-touching loops. Non-touching loops. Sum of gain product of any two non-touching loops. Minus sum of, and so on, sum of gain product of any three possible non-touching loops. Non-touching loops. What is del k? Del k. Suppose del 1. What is del 1? Same as that of delta. Same formula. So 1 minus sum of individual loop gains. Okay. The sum of individual loop gains. That means the gains, the loops which is not touching with the first forward path. Suppose kth forward path. So sum of individual gains, loop gains which are not touching kth forward path. The same sentence, which are not touching the kth forward path. This is applicable to all deltas. Kth forward path. So minus, then plus sum of the second data. Here, sum of gain product of any two possible combination of two non-touching loops which are not touching the kth forward path. That is, so for all the not touching the kth forward path. Kth forward path. Understand or not? So this is the simple easiest way of determining the transfer function of the system.